Okay, so we're going to cover another section of 3.2 here, and we're going to be talking about the standard deviation of residuals, which is your lowercase s. We'll also be talking about our coefficient determination, which is your r squared. Talk about some outliers and how they affect the least squares regression line. So again, let's look at this right here on our big ideas. We've got standard deviations of the residuals, or lowercase s. Right there next to it, as far as the TI Inspire menu directions on how to calculate that. Then we're going to go into the coefficient of determination, which is r squared. And then right there next to it as well are the TI Inspire menu directions. Down here at the bottom, where it says, where we have our graph and whatnot, with our good least squares regression line, has a low standard deviation of residuals and a high coefficient of determination r squared. So let's think about that before we talk about those a little bit. For standard deviation of residuals, you have interpretation. Is the actual y context value is typically about your s, the value you get for your standard deviation of residuals, away from the number predicted by the least squares regression line. So if you have a low value with that, the lower the standard deviation between those residuals, the more fit the line is, the less of a gap of line in between the actual point and the predicted point. So the overall standard deviation between each of those residuals is better to be a low value. The coefficient determination. So about the coefficient determination percentage of the variability in the y context you're talking about is accounted for by the least squares regression line. What that is meaning, as far as saying that least squares regression line is getting a percentage of the values that are landing on that line. So if you have a high coefficient of determination, therefore that means you have more data points that are falling on your least squares regression line, which are giving you a better fit line. So therefore that's why you want to have a low standard deviation of residuals, to where there's not much space between the actual and the predicted. And therefore that would also give you, if that is low, then that means most of those lines are probably going to fit and actually touch that line. So the percentage of data points that fall on that line is going to be high. So that is why it says a good least squares regression line has a low standard deviation of residuals and a high coefficient of determination. And we'll play around with that here in a little bit. The last thing we'll look at today is talking about the least squares regression line and the equation. So you have your y hat equals your b sub 0 plus your b sub 1 times x. Your b sub 0 is your y-intercept, and your b sub 1 is your slope. Then we go through the equations there, which we're talking about, as far as dealing with, to find your slope, your b subscript 1, it's equal to your r, your correlation, times the standard deviation of y divided by the standard deviation of x, which you will have those values to calculate. And for your y-intercept, b subscript 0 is equal to your y mean minus b subscript 1 times your x mean. All right? Therefore, that will give you the y-intercept of the equation for your least squares regression line. So let's look into this. 5 students requested that the counselors update their transcripts for them. Adam, Bernard, Christy, Deja, and Eldon. Their IQ scores are 110, 85, 120, 95, and 105. But they have been all mixed up, and the counselors don't know which IQ score goes with which student. The guidance counselors are forced to predict the IQ for each student. Each counselor takes a different approach. So we're going to look at this for counselor number 1, which is the new guy. So the new guy is so nervous about being wrong, he wants to play it safe with his predictions and minimize his error. He decides to find the average IQ and use it as a prediction for all 5 of the students. So if we go through this and do an average of those 5 values up there, which are 110, 85, 120, 95, 105, that comes out to be an average of 103. Counselor number 2, the veteran counselor, noticed an equation written on the board in the AP statistics. So IQ equals 16 times the GPA plus 57.3. She realized that GPA can help her to make better predictions. She looks up the GPA for each student. So the GPAs are given below. So then we simply need to take these GPAs and plug them into that equation. And we get these values. So we get 86.1 for Adam, Bernard has 95.7, Christy has 103.7, Deja has 111.7, and Eldon has 118.1. The third counselor, the truth seeker of the group, pulled the 5 students out of class and found out the truth. So therefore, they got the actual IQ level for each one of them, right there. Who made the better predictions? So let's see here. With counselor 1, the new guy used the mean IQ for every prediction. So with this, predicted was 103 for everything. So now we need to find the error, which is your actual minus predicted. And then we're going to square those values. Now that we've squared all those values, let's go ahead and add them up. And that comes out to 730. So now let's look at the counselor number 2, the veteran who used the line of best fit for the predictions. So with this one, the data we had up above for the predicted IQ. So we had those data points. So now let's look at our error, actual minus predicted with these. And now, as we did on the previous one, we're going to square all those errors. So all I did was take each one of these error values again and squared it here for the bottom row. So let's go see what we get for our actual sum of those squared errors. And that comes out to be 89.89. So let's think about this. Who did better and why? Well, looking at it, it should be the veteran did better, because her sum of the squared errors, which was 89.89, was less than the sum of the new guy squared. So again, we'll say the veteran because her sum of the squared errors, which was 89.89, was less than the sum of the new guys. And right there, as we said above, we had 730 for counselor 1, and the sum of those errors was 89.89 for number 2. That's all I was asking there. So now it wants us to calculate the percentage improvement of the sum of the squared errors from guidance counselor number 1 to guidance counselor number 2. So to go from guidance counselor 1 to guidance counselor 2, let's go ahead and use the values that we have for these guys. So the squared errors. So we know we had counselor 1 had 730, and we're going to subtract counselor 2's squared errors of 89.89, and then to get our percentage, we want to divide that by our counselor 1, which is 730. So you should get, I think it comes up to be 641 over 730, which equals your 0.877. Okay? So that's a percentage improvement of the sum of squared errors from guidance counselor 1 to 2. Also could find each counselor's typical error. So using algebra to turn the sum of the squared errors into the average error for guidance counselor number 2. Squared errors was 89.89. And how many kids did he have? He had 5, so we divided by 5. What's the other trick here? What is the typical thing we're talking about here? Squared errors. Squared errors. So we would need to take the square root of that value to find what we're looking for. And this should come out to be 4.24. So in which case, this means average error for guidance counselor number 2 was 4.24. Now let's find the correlation, the coefficient of determination, and standard deviation of residuals for the data using a calculator. Now, I know we all don't have calculators all the time, but I'm going to show you how to do this in Google Sheets as well. In Google Sheets here, I've already put the data that we had here. We had our GPAs that they gave us and the actual IQ values. First off, if you need to find the correlation, which is your R value, that is easily done as well in here. You can go up here and type out equals and then CORR, and then right there it pops up CORREL. Right, then it wants you to put in the Y data, comma, and the X data. So by clicking highlight the Y, comma. I'm gonna click and highlight the X values, close parentheses, enter. And that is going to be our correlation. Now, we need to find our coefficient of determination. Well, to do that, we need to go ahead and make a graph here. So let's go ahead and take these values and highlight them all. And highlight from the top here, from the GPA all the way down to 120. All of them there. Now I'm going to come over here, I'm going to click on the Insert Chart button. In which case it already put a scatter plot for me. So you should be able to click on the setup under the chart type up here and select what you want. It suggested a scatter plot, which is what we need. But if you need to, you can always scroll down, and it's down here as well to select if you needed to. But we're going to do scatter plot. Then I want to click on Customize and click on Series. Let's add a tread line. Alright, so that's going to be like our least squares regression line right there, okay? And then you come right down here and click on Show Coefficient of Determination. And it gives us that value right there. So it tells me that we should get 0.877. Well, if we go back here and look, right above here, that's what we got for our percentage improvement, right? 0.877. So that works out good. And let's go ahead and write our correlation here we had. And our correlation was 0.936. To calculate our standard deviation of residuals, our S value, I'm going to have to use the TI Inspire for that. So on the home screen here, I'm just going to go to Spreadsheet. And we're going to enable this. We had as far as GPA. And then we had our IQ. All right, so once you have all that data in a spreadsheet there, then you're able to just come over to any empty cell. Now that I've highlighted an empty cell there, let's go ahead and do what it says in our big ideas. So we're going to go to Menu, Statistics, Confidence Intervals. We're going to go to Linear Reg T Intervals. Slope, okay. Our X is our GPA, our Y is our IQ. Click OK, everything else should be fine. And here we get our value for a standard deviation of the residuals, which is 5.47. So if that is our standard deviation of residuals, why is it different from here? Shouldn't we have gotten the same setup here as far as looking for our squared errors, or our average of errors, should we say? So with that, the reason why is because in the calculator, the actual function, instead of dividing by just 5, you would simply divide by n minus 2. So if we were to do this by taking, so let's take the square root of 89.89 divided by 5 minus 2. Then we should get 5.47. So 5.47. So we would have got the same setup there, but the actual calculation for the statistics calculation is to take your sample size minus 2. All right, so now we're just going to play around and have some fun with this one. So we're going to play with some outliers and see how it affects our least squares regression line. So let's go to Staplets, all right? And when you get here, you can scroll down and you want to click on Applets for the Practice of Statistics 6th edition. When you click on that, this site right here, scroll down and we're going to look for the correlation and regression. So applet for correlation and regression is right down here. When you click on that, we're brought to this page right here. Now, But looking at this page, we just want to do this little exercise here. So it wants us to put 10 points in the lower left corner, so the correlation is about 0.4. Then we're going to check boxes to show least squares regression line in the X and Y lines, and in which case we would normally sketch it here. But then I'm going to go through the status of playing around with some outliers and see how that affects our least squares regression line. So we're going to put 10 dots down here. Alright, so there's 10 dots, around 0.4. Let's go ahead and show the least squares regression line, and then show the X and Y line. So now, to play around with this, what it wants us to really do here is place a dot way out here, on our x-axis, way far away, and see what happens to our least squares regression line. It changes it quite a bit, right? So our slope decreases dramatically, and our y-intercept increases, and our correlation value over here, that decreases as well. Now once you've made a dot over here, to get rid of that dot, you can just click on that dot again to make it go away and get us back to where we were. So let's see what happens when we put one maybe on the far left side. Way over here. I'll do it again as it changes kind of fast. So again, the slope decreased, the y-intercept increased, and then the correlation decreased on us again, because the correlation went from 0.4292 to 0.37, around that range, okay? As you can tell here, the y-intercept is jumping up, and the slope is decreasing. Alright, so let's see what happens if we put a dot way down low. Well, if we put one below, the slope stayed the same. Our y-intercept decreased though, it dropped it down a little bit. And the correlation decreased as well, as we saw. So again, I'll click that button again, make it go away. So as you can see, our correlation jumped up to 0.492. We click, put our dot down here again. Correlation jumped down to 0.3507. And as you can tell too, our line is not changing as far as the slope, staying constant. However, the y-intercept is decreasing, okay? Now let's take one and put one way above. Well, there we go. So put one way above the slope. The slope should stay the same. Our y-intercept increased though, it elevated that y-intercept, and the correlation decreased as well. So again, right down there, our y-intercept increased, our slope stayed the same, but our correlation went down. So you can play around with these and definitely play with what does what with the outliers and how it makes the slopes change, your correlation change, the y-intercepts, how they interact with things. So you can play around with it. It's just a fun little applet just to play with, okay? So one other question it had here on the setup was it asked, after playing around with some of these dots, which outlier had the greatest impact on the least squares regression line, the vertical or horizontal outliers? And you should have seen that the horizontal ones had more of an effect because the more leverage on there, since they were left and right of the center. So again, the horizontal, because they have more leverage since they are to the left and the right of the center of the plot. So they're pulling that slope down, pulling it up, making that y-intercept change quite a bit. All right. Well, I hope you learned a little bit of something today. And don't forget about the last little thing that we didn't really touch too much on in the lesson here. But when we're looking at this, don't forget about these equations over here when you're having to calculate your y-intercept or your slope for your least squares regression line, okay? All right, guys, so I hope you learned something today, and I'll see you next time.